and Keaton. So yes, now we are going to move on to the second part of the talk, which is a crash course on optimal transport, because I didn't know how familiar the audience is with optimal transport, and we really require some familiarity with optimal transport before we are able to talk about Wasserstein embeddings and slice Wasserstein embeddings for graph learning. So I thought that this is a good point to dive a little deeper into optimal transport and familiarize ourselves with it. So where we left off in the past part of the talk was we talked about the blueprint for deep learning in general, and then specifically for learning from graphs and sets. And we said there are a composition of these permutation equivariant blocks with a permutation and followed by a permutation invariant block. And this whole thing is going to become, this whole operator is going to become a permutation invariant operator. Okay. And then we talked about towards the end, like, what is this permutation invariant operator? And we said a very common practice in the literature is to simply use a global average or global or simply sum pool of the node embeddings, of the output of the equivariant operator. And we said that, hey, here it's essentially like comparing the distributions based, these means are essentially the first moments of these distributions, and we are comparing graphs based on their first moments of the distribution of their node embeddings. Okay, and what can we do better? And why don't we use distances? And in general, any distances we can use. There are many distances between probability distributions. Why can't we use some other distances as opposed to just the difference between their first moments? And of course, then we can immediately say, hey, there are many classic dissimilarity measures, many classic divergences and distances between distributions, and we can use any of those. So here, just a little bit of notation. I try to be consistent, but I am not as rigorous as, I'm not a mathematician, so I'm not as rigorous as mathematicians, but so I try my best. Let's say, or mu and nu are Borel probability measures with finite pth moment defined on our domain X, which is a subset of Rd. And then we are going to define corresponding densities P and Q for this mu and nu. Okay. Then we can ask ourselves, what are some dissimilarity measures or distances between these distributions? And we can say, hey, okay, we can simply use an LP metric to define a distance between two distributions, Px and Qx. Or we can look at symmetric chi-squared distances, or Hellinger distances, or Jensen-Shannon divergence, which is a symmetric form of the KL divergence. These are emerging from information theory mainly. And we can in general have phi divergences to compare these distributions. And so all these distances or dissimilarity measures, the reason I'm hesitant to use distances is because some of them are not true distances. Some of them are not true metrics, like the Jensen-Shannon divergence. It doesn't satisfy the triangle inequality in this specific case. But so we can immediately see that all of these methods, what they're doing is they are comparing these distributions in a bin-wise manner. So if you're looking at P at X and comparing it with Q at X, okay. So then all of these are going to tell us that the P and Q1 are more dissimilar compared to P and Q2. Okay. And this might be fine in a lot of applications, but it is certainly not fine in certain applications that we will see. So essentially, this is the green distribution is simply a shifted version of the blue distribution. If we were able to fix this shift, these two are exactly alike. And because of this bin-wise nature of these similarity measures, in machine learning, they become problematic. And I need to choose my words very carefully here. But what do I mean by being problematic? So say we have two distributions here. There are two truncated Gaussians. Okay. And then assume that we have our distribution P, and distribution Q is simply a translated version of distribution P. Okay, so we have Q tau, which is simply the translated version of distribution P. And we would like to find the optimal tau that matches these two distributions, right? Then if we use any of the mentioned distances or divergences that we saw in the previous slide, and look at the distance as a function of tau. So when we are far away and then we get close by, we immediately see that when the domains of, or the support of our distributions are disjoint, these distances are going to all give us a maximum value, right? All of these distances are going to give us a maximum value, and this is going to be a constant value. There's only information when the support is not disjoint, and we get some information about like how close they are when we start having some overlap between these distributions. Okay, so this is a typical behavior of these distances that we looked at. So what are some of the implications? Well, the implications are that now we are not able to tell if the blue distribution and red distribution are closer to each other versus the blue distribution and the green distribution, because the distances are the same among them, right? So the underlying geometry of this space is not captured by these common and statistical distances. So what is the implication? The second implication, it's that if we are, for example, running a gradient descent, excuse me, running a gradient descent to find the optimal tau, we didn't initialize this correctly, so we initialized these two distributions in a way that their support is actually disjoint. We have zero gradient information. So if you're starting here, there is no gradient information for us to guide us to the correct solution. Okay, so this is implication 2. But why do we care? And specifically for implication 1, if you think about these node embeddings that we talked about, they are the distribution of endpoints. We have empirical distributions. We don't have access to the underlying distribution. We have endpoints in a d-dimensional space, and very high, with high likelihood, we have non-overlapping supports between these distributions, right? So we really, if we want to really compare this, the distances between these empirical distributions that we have, it's really not clear how we can use these distances. Okay, and then when we look at the Wasserstein distance, the two Wasserstein distance, we see that this problem goes away completely. Why? Because the Wasserstein distance, which is born from the theory of optimal transport, which we will talk about, is actually morphing one distribution into the other, or transporting one distribution into another, and then it measures what is the amount of work that I need to do. If I'm efficient, what is the amount of work that I need to do to match these two distributions? Okay, and of course, if you're farther away, you're going to do more work to match these two distributions, right? So now, these problems that we mentioned with some of the classical metrics and divergences goes away when we talk about optimal transport-based distances, and specifically the Wasserstein distances. So now we are going to essentially use that as a motivation for understanding what optimal transport is and what it does. And optimal transport is not a new problem. It's a problem that was first studied in the 18th century. So I like to call it the 18th century math for modern machine learning. And it has become very popular in the machine learning community in the recent years, and specifically in deep learning. Okay, so what is optimal transport? Optimal transport, the optimal transport problem seeks the most efficient way of transporting one set of distributions, one distribution of mass into another distribution of mass. So here we are assuming that we have three particles located at x1, x2, x3. This is our distribution 1. And three particles located at y1, y2, and y3. They have equal mass. Let's say each one of them has a mass equal 1. And we would like to transport x's to y's. Of course, there are many ways that we can do, we can plan to transport our mass from x's to y's, right? One is take x1 to y1, x2 to y2, x3 to y3, and that's going to give us a transportation plan that looks like that, right? x1 to y1, x2 to y2, and x3 to y3. We could have had other transportation plans. We could have matched x1 to y1 and x2 to y3 and x3 to y2, and so on, right? Or we could have had a situation that we don't have an equal number of particles. So we have 2 particles on one of our distributions and 3 particles on the other. And here we have a situation that the total amount of mass is equal. So we have equal mass in 2 distributions. Here the total mass is 1. But now we have to essentially split the mass in x2 and carry it to other points in y's, right? So now our transportation plans are going to look something like this. x1, the 1/3 is going to go to y1, x2, 1/3 of this amount of mass, 1/3 amount of mass is going to go to y2, 1/3 amount of mass is going to go to y3, right? And so on. We can essentially have other types of these transportation plans. Or we could have had, we could have splitted both of these mass particles and carried essentially everything to everything in this case. So we can see that there are infinitely many transportation plans that we can have to transport one set of mass distribution to another. And optimal transport is asking this question of which one of these is the most optimal way of transporting mass from the blue distribution to the orange distribution. So a little bit of a historical note. The problem was originally studied by Gaspard Monge in the 18th century. Monge was working with Napoleon at the time and was interested in the most efficient way of transporting dirt from one location to another location. I believe it was as you can see from the title, the note on land excavation and infill. And of course, like a very natural notion when we're talking about excavating land and then infilling like other areas is the cost of transportation. The mass is heavy, and like you don't want to carry like heavy mass for long distances because that's going to be inefficient, right? So nevertheless, like this was the problem that he was studying at the time. And almost 200 years later, Leonid Kantrovich was working on optimal allocation of scarce resources during World War II. He revisited the optimal transport problem in 1942. Actually, he was not aware of Monge's work at the time, but he treated the problem as a resource allocation between a set of supplies and set of demands, and how do we do the supply demand balance with the least amount of transportation cost. It's worthy to note that Kantrovich, together with Koopman, they won the Nobel Prize in Economic Sciences for their contributions to the theory of optimum allocation of resources. And actually, like the invention of the linear programming was rooted in this optimal allocation of resources as well, which is interesting from a computer science perspective. And the linear programming, the term linear programming was coined by Koopman. Okay, so now that we know a little bit of history and a little bit of high-level idea of what optimal transport is, let's first focus on defining the problem. I'm going to use the Kantrovich formulation and define the optimal transport for discrete distributions, because I think that's easier to do, easiest to follow for those of you who are not familiar with the topic. And then we will move on to the continuous Monge and then continuous formulation of optimal transport. So we looked at a lot of the different types of transportation plans. And so let's first focus on the common traits of these transportation plans. What are the characteristics that these transportation plans must have? Of course, we can immediately see that if we sum these transportation plans along the columns, we are going to get the distribution of our Q's, 1/3, 1/3, 1/3. And if we sum them along the rows, we are going to get the 1/3, 2/3, which is the distribution of our P. So we immediately see that the marginals of this transportation plan should be equal to the amount of mass in our source and target distributions. Or so we can think about the transportation plan as a joint probability distribution with marginals equal to P and Q. Okay. And then, sorry, this is a little dense, but let's see what we have here. So we are going to have our distributions to be essentially the empirical distributions that we have. We have amount of mass Pi located at Xi. Delta here is the Dirac measure centered at Xi. So we have mu and nu representing our probability measures. And then gamma ij, gamma is our transportation plan, and gamma ij identifies the amount of mass that's being transported from Xi to Yj. And then this is a key ingredient, there is a transportation cost from Xi to Yj. Think about it as gas price. If you want to go from one location to another location, you need to spend some gas, right? And that's the transportation cost that you have from Xi to Yj. We are showing it as C of Xi and Yj. And then the optimal transport problem, having all these ingredients ready, now we can define the optimal transport problem as the most efficient transportation plan with respect to cost C. So we can look at all our Xi and Yj's and the amount of mass that we are taking from our I to J. So this is going to essentially be our expected transportation cost. We would like to minimize that expected transportation cost. And of course, our constraints are telling us that this transportation plan is a joint distribution, or it has marginals that are equal to the original mass in source and in the target. But what if we had a continuum of masses as opposed to just having these particles that we talked about? Well, when we had these particles at x1, x2, and y1, y2, and y3, we looked at our transportation plan, and the transportation plan was this discrete joint distribution supported on the combination of x and y's, right? And now, if you have a continuous distribution of masses, so we have a probability measure mu and nu, they are continuous, then we can still define a joint density here. And this joint density is going to be a continuous joint density with marginals equal to the continuous one, in this case, one-dimensional distributions that we have. So there is a continuous formulation of the Kantorovich problem. And if we want to look at the general formulation, which is true both for continuous and discrete, we define a transport plan between measures mu and nu, defined on x and y, to be a joint probability measure gamma that has marginals equal to nu. So gamma of x and a is going to be nu a, and gamma of b and y is going to be nu b, where a and b are Borel subsets of x and y. And then if we define our transportation cost C to go from x times y to r, then we can define our Kantorovich problem as exactly the minimum expected transportation cost. So this is our expectation of transportation cost. And then our transport plans are joint distributions with the marginals as we defined. So this is our constraint. So just to put this all together, we see that here we have the Kantorovich problem in the discrete form. The point to take home here is that we can essentially split mass and carry it in this gamma ij, which is a transportation plan, is going to tell us how much mass is being moved from xi to yj. And our constraint is telling us that it's a mass preserving operation. We are not creating or destroying mass. The total amount of mass is constant in this transportation. And we said that there's a continuous version of that, and we looked at the continuous version of the Kolouri problem as well. Okay, so now we can talk about the Monge formulation, which is slightly different. By the way, I forgot to mention here that in the discrete setting, this optimization, we can immediately see that it is convex, although not as strongly convex. And it has linear constraints. So this is a linear programming optimization. And there are solvers to optimize this optimization problem, like simplex or the interior point methods to solve this optimization problem. Okay. So if what we learned about Kantrovich, then what was Monge doing? Like almost 200 years before that. So Monge was really interested not in the transportation plans, but in transportation maps. So Monge was trying to find a function that matches our x's to our y's. Okay. So here, then we can immediately see that we need to have, like, if you are in a discrete setting, we need to have equal number of point particles with equal mass from our x's and y's. And the problem is really like, what is the right permutation? Which x's should be matched to which y's? And that's going to define our transportation map. And we are asking, like, among all such permutations, which one should we choose to minimize the cost? Sorry, this needs to be the transportation cost C. I'm just using D as a distance here, but this is essentially our transportation cost. And in a continuous setting, this transport map that goes from X to Y is a map that satisfies the following. F push forward of measure mu should be equal to measure nu. Okay. And we would like to find such Fs, such transportation maps that minimize the transportation cost, the expected transportation cost. So, and that's the Monge problem can be formulated as minimizing the expected cost of moving mass from X to Fx. And its expectation is done on or source distribution, measure mu. And then the constraint is F push forward of mu is nu. And what does this F push forward of mu is equal to nu mean? This is essentially telling us that the mu of F inverse of A is equal to nu of A, where A is any Borel subset of or Y. Okay, and here we are depicting this with the graphics, right? If we have set A, a Borel subset A of or Y, we look at the pre-image of F, which is F inverse of A, then the mu of this F inverse, the amount of mass that we have here, should be equal to the amount of mass that we have over there. Right? That's all that it is. Of course, we can immediately see that this transportation map does not necessarily exist. So an example is if we have, or mu is a delta, a Dirac function, and then our nu is simply a Gaussian probability measure, then we can't find a map that maps this Dirac to a Gaussian, but in the reverse, this is true. We can find a map that matches a Gaussian to a Dirac. Okay, so for this transportation map to exist, we require the source distribution, or mu, to be absolutely an absolutely continuous measure with compact support. And we also require our cost to be convex. Okay. But interestingly, when the optimal transport map exists, we have an equivalence between the Monge formulation and the Kantrovich formulation, right? So, and what is this equivalent or equality? We see that the amount of this expectation with respect to optimal transport plan is equal to the same expectation with respect to the optimal transport map. Okay, which is useful, as we will see in a few slides. Okay, I need to speed up a little bit. And then, of course, there are many interesting theorems out there that talks about the uniqueness and existence and uniqueness of this transportation map. For example, we have Bernier's theorem that tells us that if our transportation cost is simply the L2 distance between x and y, 2 squared, then and our mu is absolutely continuous, then a transport map exists, and it not only exists, but it is unique, and it is characterized to be a gradient of a convex function, or we can think about it as identity minus gradient of a concave function, which is going to tell us that this transportation map is going to be a curl-free vector field, curl-free function. Okay. Any questions? Okay, so if not, I'm going to go to the next slide. Excuse me. We talked about the Kolouri primal problem, and it looked like that. But then there is a dual formulation for the Kolouri problem. We have the Kolouri dual problem, which, as opposed to minimizing over the transportation plan, we are maximizing over two functions phi and psi, and we are maximizing the sum of their expected value with respect to our source and target measures. And then the constraint is telling us that phi x plus psi y should be smaller than or equal to cxy. Okay. So when our cost function is the L1 distance, this dual problem is actually very common in machine learning. And it's called the Kantorovich-Rubinstein formulation of optimal transport. And if any of you is interested in generative modeling, generative deep neural networks, and Wasserstein GANs specifically, that Wasserstein GAN is exactly using this dual formulation of the Kolouri problem using this L1 transportation cost. Okay. And so the equality holds between this. So this dual is always smaller than or equal to the primal, and this equality holds when the cost function cxy is non-negative lower semi-continuous. And I just thought that for the sake of completion, it's important for us to know the dual formulation as well, specifically because in deep learning and machine learning, this is a very common formulation that we use. Okay, so far we have talked about optimal transport, but the title of my talk is Wasserstein embedding. So what is this Wasserstein distance or Wasserstein embedding that we are going to talk about? Well, the optimal transport, the theory of optimal transport gives birth to the Wasserstein distance, which is a distance between two probability measures, right? So what is this Wasserstein distance? If we simply define or calculate our optimal transport problem and look at the minimum value, given that our cost is d to the p, and the only thing that we require is that this d is a distance between x and y. And so we have d to the p to the power p, and then we calculate this expectation and calculate the pth root of this value, then that's equal to the p Wasserstein distance between these two probability measures, mu and nu. So again, what is this optimal Wasserstein distance? This Wasserstein distance is literally the output of our optimal transport map, the expected cost of our optimal transportation map or optimal transportation plan. Right. So going back to that problem of two Gaussians with two truncated Gaussians that we had, we can immediately see that to be able to calculate this distance, we actually need to transport one distribution into another and measure how much transportation we have done. And that's why the farther we go and the more the farther we have these two distributions, the higher the Wasserstein distance is going to be. And then this, of course, you can appreciate that this is the Kolouri formulation. And if we have our distributions to be continuous, then we can immediately write the Monge formulation of a Wasserstein distance and calculate the Wasserstein distance by the Monge formulation as well. Okay. And so one important point here is, as we said, counter-rich formulation is a linear programming optimization problem. I mentioned that there are solvers to solve this optimization problem, but these solvers are often not computationally efficient, right? So if you have n number of particles in our two measures, we have n cubed log n as our computational complexity to calculate the Wasserstein distance. Now, there has been a lot of work on making this calculation faster. In particular, the entropy regularized version of this objective function has become very popular, and that reduces the computational complexity to n squared log n. But nevertheless, that's still quite expensive in a lot of machine learning applications where the number of particles grows. For example, in graphs, when we're comparing different graphs, we can have many, many nodes in these graphs, right? So n can be very large. But a good news is that the P-Wasserstein distance for one-dimensional distributions can be calculated very efficiently. Okay, so let's look at this for absolutely continuous probability measures, and then we will see it for discrete measures. If we have one-dimensional distributions mu and nu, we can essentially define the optimal transport map F star as a composition of the inverse of the CDF cumulative distribution function of one with the cumulative distribution function of the other. Okay, so this F mu and F nu are simply the cumulative distributions, right? Defined as mu of negative infinity to x and nu of negative infinity to y. And then the P-Wasserstein distance can be simply calculated as the distance between the inverse of these CDFs, these cumulative distribution functions, right? Or the quantile functions, sometimes called the quantile functions in the statistics. So there is no, one thing that to notice here is that there is no optimization, there is no minimization, because this F star is uniquely defined. We don't need to calculate any optimization here, and we have a closed form solution for Wasserstein distance. And what is it measuring? So think about this I0 and I1 as the densities that we have, and we look at their CDFs. This is the CDF of the blue distribution, the CDF of the red distribution. And simply, if you look at, compare these two along their inverse, so we need to really think about their inverse. But if we think about Wasserstein one distance, we are measuring the area between these two CDFs, or the area between the inverse of the two CDFs. And you can immediately see that when we go farther away from, the distributions go farther away from each other, this area becomes larger, right? And that's why the Wasserstein distance grows. So in, for discrete samples, which is like quite commonly used in machine learning, we can simply see that to calculate the Wasserstein distance between these two empirical distributions, all we need to do is to sort our samples from distribution source, sort our samples from distribution target, and then match our samples one by one, assuming that there are equal number of mass particles in these two distributions. Okay, so calculating the Wasserstein distance in this case boils down to two sorting operations, and it can be calculated very effectively. Okay, but this is only true for one-dimensional distributions. What can a one-dimensional distribution?
I'm sorry, I have a question. What do you mean by sort here? What are you sorting? I mean, how? I'm not sure I understood.
Right. Okay, yeah, let me quickly look at the continuous versions first, right? So let's say I have these continuous distributions, distribution 1, distribution 2. I look at their CDFs here, and I look at, I want to calculate this term, the difference between the inverse of their CDFs, and I want to calculate this integral numerically, right? So if I want to calculate this integral numerically, what I need to do is I need to quantize my 0 to 1. Remember, these are the CDFs, and now I'm trying to measure the difference between the inverse of these CDFs. So I go and I quantize my 0 to 1, right? And to calculate that that integral, I'm simply going to have essentially evaluate this F inverse for the blue point here and F inverse for the green point there, and measure this distance between them. And then I have the delta that I use to quantize my domain, right? And then let's say I used this quantization is done in 5 periods, right? Five regions. And then I simply calculate the areas of these rectangles, right? To numerically calculate that integral. Now, if we go to the case that I had 5 samples from this distribution and 5 samples from another distribution, right? These are arbitrary samples, like I just sampled these points from my distributions. If I want to approximate that integral here, based on these samples, these 5 samples that I have, so what's going to happen is I'm going to essentially look at the CDF of this and CDF of that. And these CDFs are going to be like, let's say the mass is 1/5 for each one of these. So the CDF is going to look like this step function, right? And I have the same step function for the orange point.
Okay.
And then to calculate essentially exactly the same thing that I was doing up here, these rectangles, I need to go and simply say, where was my first sample? Where is my first sample for the other one? Measure the distance between these two, and then multiply that by this one.
Okay.
So that means that I had to essentially sort these points in an increasing manner. So sort x's in an increasing manner, sort y's in an increasing manner, and then measure the distances between the sorted versions of x's and y's 2 by 2, and then sum that up. And that will be the approximation of my Wasserstein distance, or this integral that we're talking about.
Right. Thanks.
So, and sorting can be done in n log n. So if you have n points here, it can be done n log n. So I do n log n, and after that, I essentially simply calculate the Euclidean distance between these sorted versions, and that gives me the Wasserstein distance. Okay, but this is only for one-dimensional distributions. It's really not that interesting for learning, like we usually deal with higher dimensional distributions. What can we do to leverage this one-dimensional closed form solution of one-dimensional, closed form solution of the P-Wasserstein distance for one-dimensional distributions? Well, we can rely on computational tomography a little bit. And so for those of you who are familiar with radon transform, that's commonly used in computational tomography. And the idea there is that we can always slice high dimensional distributions into their one-dimensional marginals and into infinitely many one-dimensional marginals. And then we can always also recover that n-dimensional distributions from these infinitely many one-dimensional marginals. Okay, so that's the idea proposed by radon, and which we use in computational tomography almost everywhere in these days, right? So how do we formulate this? Let's say we have our distribution, px dx is essentially our d mu x, right? So we have our probability measure mu, it has a density p, and I'm just simply writing the integral as with respect to the density and Lebesgue measure here. And then we are going to integrate our d-dimensional distribution along hyperplanes that are orthogonal to a unit vector theta. So theta is a unit vector. And then that's going to give us a one-dimensional distribution for all t's. So let's see what we mean. I think it's easier to look at it visually. Say our distribution is a two-dimensional distribution, and we are going to integrate this two-dimensional distribution along all hyperplanes that are orthogonal to theta. And of course, each one of these hyperplanes is going to have have a value t, which is the inner product of all the x's on one of these hyperplanes and the theta, right? And so if we do this, we are going to get a one-dimensional distribution as a function of t, right? So this two-dimensional distribution was sliced into this one-dimensional distribution. Of course, it depends on theta, the theta that we chose, and then the variable that we have for that one-dimensional distribution is t. And then we can choose another theta, and we can slice or two-dimensional distributions along that, another theta, another theta, another theta, right? And then it turns out that we can recover our two-dimensional distribution from these one-dimensional slices. Okay, so this is the idea of radon transform. Now, this idea is also extended to generalize the slices or generalized radon transform. Gregory Belkin did that. And essentially, as opposed to having a simple inner product here in our delta function, we have a parametric function g theta, and this parametric function needs to satisfy a bunch of regularity conditions that I'm not going to go into. From a geometric perspective, what's happening here is that we are not integrating our distribution along hyperplanes any longer. We are integrating them along the level sets of a nonlinear function, right? So this G is going from RD to R, right? And or equivalently, we could have said we are integrating our d-dimensional distribution along hypersurfaces, d minus one dimensional hypersurfaces in this d-dimensional space, and that's going to give us a marginal distribution or one-dimensional distributions with respect to theta again. Okay. So what is this? Why is this useful, and why are we talking about it? Here, so by the way, just very quickly, this is another visualization of the integration of two-dimensional distributions. This is if we do linear slicing or the radon transform, we can essentially have nonlinear slicing. These are the level sets of that g theta function that we were looking at. We can integrate our two-dimensional distribution along those and get a different marginal. Or these g thetas can become much more complicated. Here we are actually using a neural network with some regularity conditions to generate these. But nevertheless, you can generate these one-dimensional distributions. And if this g theta satisfies some conditions, you can recover your two-dimensional distributions from infinitely many such one-dimensional slices. Okay. Now that we have this notion of slicing d-dimensional distributions into one-dimensional distributions, we can define the sliced or generalized sliced Wasserstein distances, which is telling us that let's calculate the Wasserstein distance between these one-dimensional distributions or two-dimensional distributions, and calculate the integral of all of these Wasserstein distances between one-dimensional distributions. So in a discrete case, let's say we approximate this integral only with L slices. So we are going to have an average of the Wasserstein distance between these one-dimensional distributions, each one of them being the Lth slice of P and Q, right? So if we have two distributions, this, by the way, this can be implemented in a parallel form, like so you can have this summation being implemented in parallel. So you have L processors or K processors in this case. Each one is going to slice the d-dimensional distribution into one of the marginals and calculate the Wasserstein distance, which is simply an n log n operator, and then aggregate all of them or average all of them into the sliced Wasserstein distance, or an approximation of the sliced Wasserstein distance, because we only used L slices as opposed to infinite number of slices. Okay, so this is one very interesting way of calculating a transport-like distance, this sliced Wasserstein distance, for high-dimensional distributions. That's significantly cheaper to calculate compared to the original Wasserstein distance. Okay, and so the last point that I wanted to talk about, maybe I go over it in 2 minutes, is the geodesic, although maybe it's not super relevant to the topic that I'm going to talk about next, but I thought nevertheless it's important to know about Wasserstein geodesics, because it's very useful in nonlinear modeling of two-dimensional distributions or and three-dimensional distributions in biology. It's used there commonly. So very quickly, if we have the two Wasserstein space, and the two Wasserstein space is essentially the space of probability distributions with uh, with the finite second moment, and we have the two Wasserstein distance as a metric in that space, then we can talk about the shortest path between two distributions, mu and nu, on that space. And this shortest path is going to define the geodesic for us, right? And how do we formulate this geodesic? How do we parameterize this geodesic? Well, if we have the optimal transport plan F star between mu and nu, we can simply calculate a convex combination of identity X and F star and call that Ft. And then if we look at the Ft push forward of mu and we call that mu t, we see that at t equals 0, this mu 0 is equal to mu. This is simply identity. And at t equal 1, this mu 1 becomes nu, right? Because it's essentially F star push forward of mu. And we can immediately check also that this the Wasserstein distance between mu and mu t is going to be equal to t Wasserstein distance between mu and nu. So this is giving us a parameterization of the shortest path between two distributions. And if we look at this shortest path, the Wasserstein geodesic between two distributions here in one dimension, we see that actually one distribution is being transported. It's moving along from one distribution to another. Same here in the two-dimensional space, and here for a more complex distribution, in this case faces. But if we do the same thing for in the Euclidean space and calculate the shortest path, we see a mass is going to be destroyed in one location and created in another location completely, right? So this doesn't, essentially mass teleportation is happening here, which is not, which is not respecting the underlying geometry of the problem. Okay, so and this was just a very quick recap of Wasserstein geodesics, and you can immediately, I think, appreciate the nonlinear modeling power of this versus where we have like 2 points showing up in the Euclidean geodesic. Okay, so then quickly, if you revisit our geometric deep learning problem, now we can think of, after these permutation equivariant operators that we had, we said that we are going to have a distribution of in our node embedding, an empirical distribution in our node embedding. Let's call them mu and nu, and so they're defined as follows. Like we treat each the embedding of each node as a mass particle with equal number of mass assigned with them. We can even have different number of mass assigned to them if we want, but for simplicity, I'm just using equal mass for them. And then we can measure the distance between these two distributions through optimal transport. And then the output of this operation is going to be a permutation invariance value. So it doesn't matter how we permute or input nodes, after we are comparing these distributions, the optimal transport is going to take care of that permutation by solving this linear programming problem and solving this assignment problem. So as opposed to just simply comparing the means, now we can go and we can calculate the transportation plan between these distributions. And now we can have the Wasserstein distance between the node embeddings of two graphs, GI and GJ. And as we talked about in the past, this is pairwise. This requires two graphs to be able, for us to be able to do that. But we know that if we define a similarity between graphs, here we are going to define a kernel to be simply e to the negative lambda Wasserstein distance between the node embeddings. Then this similarity between two graphs, we can use it in kernel methods like kernel SVM and kernel SVR to solve machine learning problems. And then the only thing that's kind of the bottleneck here for us is if we do it in this way, then if we have m graphs in a data set, and in average we have n nodes in the graphs, we need to calculate these pairwise Wasserstein distances. We mentioned that the Wasserstein distances are going to cost n cubed log n. And then if you're, or if you're using the entropy regularized version, n squared log n. And then, but we are going to have pairs of these distances. So we have m squared n cubed log n. This becomes problematic. We can't really, it becomes infeasible for larger scale problems. By the way, now we could have replaced this Wasserstein distance with a sliced Wasserstein distance, and we could have gotten some benefit there as opposed to n cubed log n. We could have gotten ln log n, L being the number of slices, right? But can we do any better? And this is exactly where we want to go tomorrow and in the next 2 sessions of my talk. We would like to see the Wasserstein embeddings, which allow us to actually get these distributions or node embeddings and embed them in a Euclidean, in a vector space, such that the Euclidean distance between the embedded points approximate the Wasserstein distance. And if we do it in that way, then instead of calculating the pairwise distances, all we need to do is to calculate m optimal transport problems. So this is going to be m n cubed log n. And then in the last part of the talk, which is part 4, we are going to use the sliced Wasserstein embedding. And there we are going to get m l n log n, which is the best we can do for comparing the graphs. So sorry, I ran a few minutes over time, but like I'll be happy to answer any questions.
Well, thank you very much, Soheil, for very nice lectures. Yeah.
Thank you.
Soheil, there is at least one question from the audience.
Awesome.
Hi, can you hear me?
Yes.
Hi, thanks for a very nice couple of talks. Looking forward to tomorrow. So, you know, we sort of introduced the sliced Wasserstein kind of in the context of radon transforms.
Right.
And I know that in that context, radon subsampling, doing discrete algorithms can be a little bit challenging. How do you pick the, you know, discrete numbers of directions, and then how do you sample along the lines in those directions? And I think it can get a little bit subtle. And I wanted to know if you had any comments about how to think about picking the directions for sliced Wasserstein. How many do you need for easy distributions versus hard ones? I mean, anything you could say about that would be interesting.
Yeah, first, thank you so much for a fantastic question, right? This is really going at the heart of the problem with the sliced approaches, right? Okay, so first, let's see, in 2D, if we are thinking about this radon transform, which is like usually you apply to 2-dimensional or 3-dimensional images, rarely 3-dimensional images, often 2-dimensional images. Say to be able to reconstruct your 2-dimensional distribution with some epsilon error, you require L slices for the sake of our conversation. Then if you want to increase the dimension to, let's go from 2-dimension to 3-dimension, now we immediately see that L is not enough. We need to have L squared. Okay. So what is this telling us? It's telling us that if we want to sample the unit sphere in a in 2-dimension, which is a circle in that case, and then we would like to essentially maintain the density of points on this sphere in the 3-dimension, we need exponentially more samples. We need L squared there, right? And as we increase D, we need exponentially more slices to be able to recover this. Essentially, if we go there, this L needs to exponentially grow if we want to approximate this distance accurately. Okay, so that's the problem, right? Higher dimensions, as D grows, you need many more slices. But what can we do? First, it's not very clear, because like the reason we need many more slices is because in radon transform, we would like to be able to recover the distribution. We would like this to be an invertible operator, invertible transformation. We would like to actually be able to recover the distributions. If you're talking about if you're only talking about measuring distances between distributions, maybe we don't care about recovering the distributions. So we may be able to get away from with fewer number of slices, given that we are choosing those slices in a smart manner, right? So what do I mean by that? If we just say you have one slice to choose and you would like to still get a distance here, then what would be the best slice? But the best slice would be the one that maximizes this Wasserstein distance. You're essentially saying that I have 2 distributions, find one slice that maximally separate these 2 distributions. And then that's going to give me a notion of distance, because if the distributions were aligned, even if I'm looking at the maximum Wasserstein distance, that's going to give me 0. So it's going to be still a distance, right? And that brings us to the max sliced Wasserstein distance, which is a work that was, it's not from our group, it's from UIUC, if I'm not wrong. And so that's called max sliced Wasserstein. If you think about this as an expectation of the Wasserstein distance over all possible slices, we can replace this expectation with the maximum, right? And then there are other works that are looking into like optimizing, let's say, a set of L orthogonal directions that maximally separate the Wasserstein distances. Patty and Kolouri have an interesting paper on that recently. So meaning that if you want to avoid the curse of number of slices when you go to higher dimension, you need to do a little bit of more work in optimizing and choosing these slices a little more carefully. I hope that that answers your question.
Yeah, thank you very much.
Any other questions? Okay, one from.
I missed the first talk. I don't know if there's anything that the speaker that I don't know can just inform me on that first talk, but apologies for making a disruption here. Yeah, it's I'm on your time, all of you. So I really apologize.
Sorry, I didn't hear the question. I didn't understand the question. Can you repeat?
You want to pose it now or later on? Okay.
Yeah, so I just wanted to ask, I guess, so Soheil, I'm just trying to take this as seriously as possible. I just would like to thank you for your talk and apologize again for some of the disruption. I don't know how.
Thank you.
How disrupting it was, but it's not a big deal. I think things have been sorted a bit during your talk. So thanks.
Awesome. I appreciate it. Thank you.
Soheil, if you allow me to ask a math question.
Okay.
There were several definitions, and in the definition you used minimum, not infimum. Is it because the infimum is attained, or you simply do not care about informing?
Yeah, that's a good question. And yes, so the reason is, again, I'm not maybe a mathematician or as rigorous as a mathematician should be, right? So for the case of Monge, we are talking about optimal transport. I'm assuming that we are talking about the optimal transport formula.
Yeah, for example, on page 16, if I'm not mistaken, right, there was some, but there were a couple of places. Yeah,
right.
Like
so
here.
Here we can actually, so the Counterwich problem, as I said, is a linear programming optimization problem, right? And this linear programming optimization problem is, we are essentially looking at an intersection of a plane with a, what is it called? The name is escaping my mind, but here the minimum is attainable, right? Here the reason we are using a minimum is actually the minimum is attainable here, right? As opposed to using the infimum, right? But in the case of Monge, here I'm using infimum as opposed to minimum because this does not necessarily have an optimizer, as we talked about, right? Like here is an example that we don't even have such such mapping, right? So here, the infimum is, as far as I know, right? The infimum, the minimum is not necessarily attainable. But if you're talking about linear programming, this minimum is indeed attainable.
Thank you very much.
Okay, I think one last one. So yeah.
Yep.
Thank you so much. This is a quick question. Thank you so much for your talk, Soheil. So You mentioned the slice Wasserstein distance. Is it equivalent as the Wasserstein distance? Are these metrics equivalent or?
Yeah, so they share a lot of characteristics, right? Like they share statistical characteristics, they share topological characteristics, right? And there are results from Bonil PhD thesis in 2013, I think, that shows that the sliced Wasserstein distance uppers and lower bounds the Wasserstein distance, right? So those are the things that we know. But I am hesitant to say they are equivalent. They are not. As far as as far as I know, they are not equivalent, right? They share a lot of characteristics, right? But yeah.
Thank you.
Okay, yeah, thanks, Soheil. So I guess there will be a coffee break for those of us that are in person. Oh, sorry, I guess we have one